What's going on, everybody? Mr. Gustin back in the chemistry classroom here today. We're talking about rate laws from data. We're talking about how we can use data to go ahead and determine a rate law experimentally. So today's reaction, we've got A plus 2B plus C produces D. Now we know that our rate law is dictated by products that are, or chemicals that are in our reactants typically. Sometimes they're hidden in different steps, but we always kind of start with those chemicals that are in our reactants. So let's go ahead and first go ahead and write a basic rate law. If these are the chemicals involved, we know that rate is going to be equal to rate constant times the concentration of A to some exponent X times the concentration of B to some exponent Y times the concentration of C to some exponent Z. This is our basic rate law. Now the first question we're asked here is to determine the order of each reactant. Well, orders would be like X, Y, and Z. It's the exponent on each of those concentrations. So we're going to use some data to find what the order or what the exponent is for all three of those chemicals. So we'll start with A. When I'm trying to analyze A's impact on the rate, I want to find two trials that will change A while holding B and C constant. I want to control B and C so that the changes in rate I know are only associated with A. So let's go ahead and find that first. And it looks like if I take trials 3 and 4, where B and C are constant and A is doubled, I'll be able to use these two experiments to determine the order for A. Okay? And before we actually go ahead and determine that order, let's go ahead and just say over here, we're going to use experiment number 3/4 for A. Now let's go find B. With B, we want to do the same thing. Find two trials or two experiments where A and C don't change, but B does. And it looks like from trials 2 and 3, A and C, even though they aren't equal, they don't change from trial to trial, from experiment to experiment. And from here, they're times 2. So I want to go ahead and write that down. I know that 2 and 3, those are my experiments for B. Lastly, we want to find C. So C, it looks like I'm going to be using experiments 1 and 2, because again, C does change, it doubles, but A and B do not change. So it appears that these are the reactions or the combinations of experiments that I am looking for here. All right, once you've identified those, let's go ahead and analyze some data. So I'm a big fan of always multiplying numbers out and kind of saying, by what factor does the concentration change, and therefore by what factor does the rate change. So when I go from experiment 3 to experiment 4, I notice that the concentration is doubled. All right, so concentration in my rate law is A. So I'm going to say A it changes by a factor of 2. Concentration is raised to some exponent X. That's what my generic rate law says. In my data, I'm looking to say, okay, what happens to the rate when I double the reaction? And I'm not sure. Those are pretty small numbers. I can't quite do those in my head, so I'm going to go ahead and divide them just to figure out how many times bigger this is. This ends up being 4 times bigger. So essentially what I'm saying is, in order to find the order or the exponent on A, I need 2 to some number X to be equal to 4. Now I can go ahead and do some logs or natural logs. I can do some fun math stuff here to figure this out. But I would argue that most students know 2 squared is equal to 4. Meaning that the exponent on A is a 2, or that we would call A second order. And that's the first answer for the first part of this question. Determine the order for each reactant. A is second order. And we're going to go ahead and do the rest of this data analysis for the rest of these. So let's go ahead and use trials 2 and 3 to find B. 2 to 3, we see that doubles. So 2 raised to some exponent Y is equal to 0.020 divided by, well, this is just silly. I don't know why I even divided it. 2 to some number is, I'm sorry, that's a 2, times 2. 2 to some number is equal to 2. Well, I guess I would hope most students, without having to do logs, would say 2 to the first power equals 2, which means that this exponent here is a 1, and I'm not even going to write that 1 in, but I will say that this is first order. 2 down, 1 to go. I'm looking at C, and C I already chose. We do trials 1 and 2, or experiments 1 and 2. Over here with C, I see that the concentration is doubled. All right, so 2 to some exponent Z is going to be equal to, that's the same numbers. This is times 1. So 2 to the Z equals 1. This one's a little bit trickier, but if we're pretty advanced in our high school math, we know that 2 to the 0 power is equal to 1. In fact, any number to the 0 power is equal to 1, which means this exponent is 0, which means that this is actually a 1. So C is not even in my rate law. We would call it a 0, I know, silly names, a 0th order reaction, or reactant rather. So here we go. I've analyzed my data to figure out the orders. In doing so, I've already figured out what my rate law, my generic rate law is going to be for this reaction. So I finished problem A, and I have a rate law. Let's see what the next part of this question asks me. So as I scroll down, it looks like most likely it's going to ask me to either calculate the rate or the rate law. So it does. It asks me, what is the rate law for this reaction? I already have the rate law for this reaction. I went ahead and did that while I was finding the orders. It also asks me for the value of K. It's asking me to calculate K. That's a weird thing. If I'm going to calculate the value of K, I need to plug in some numbers for rate, for concentration of A, and for concentration of B. It's almost like if only I had a table of information that allowed me to pull out rate and concentration of A and concentration of B. Oh, wait, folks, like that's what this literally is up here. This is a data table where I've got concentration of A, concentration of B, and rates. So for this last question, let's do that. Let's pull out this concentration of A, let's use this concentration of B, and let's use this rate. Let's plug those numbers in and go ahead and solve for K. So I'm going to slide this thing down here, and let's go ahead and do it. We said that the rate from above was 0.001 molar per second equals K times the concentration of A, which was 0.01. I gotta square that, times 0.01, which was B's concentration to the first power. If I start thinking this through, this ends up being really 0.01 cubed, but I'm not going to do that to us. Let's go 0.001 divided by 0.01 squared times 0.01, that equals K. And I'm not going to do the math for you. You do the math. You solve this problem. But what we're looking at here, and I'm sorry, I messed this up. This is actually 0.01, not 2 zeros. But I've gone ahead and I've used my rate law. I've plugged in rate data from experiment 1, and you can use any experiment you want. Really, any experiment you want, but I chose experiment 1. So I plug in data for experiment 1, and then I go ahead and do my algebra and I find K. Once I find K, I can plug K back into my rate law and go ahead and use that for any situation in which that reaction takes place at the same temperature and pressure. Okay? This is our basic rate law problem. It's how we analyze data. It's what I'm going to ask you to do on your summative. There's practice online. Go ahead and wrap it up, and I hope this helps. If you got questions, let me know. Otherwise, I'll see you in class. See ya.